Good. All right. Well, let's go ahead and get started. People will probably just join as we get going, but hello, everyone, and welcome to SMAP. I'm going to start by actually sharing my screen here, and we are going to be talking about citizen science specifically in astronomy and astrophysics. So citizen science is a term for research that's assisted by the public or amateurs. And I just kind of want to cover the word amateurs real quick because a lot of times it gets negative connotation. In astronomy and things like that, it's just a term for astronomers that don't have kind of professional training or education, but they're still passionate about it, and it doesn't make them any worse in any way. It's just a term that we use, but it's something that you can do that the public has done with telescopes. If we have a telescope pointing at something and it's something weird that happens, we have data from it. Or it can be even done today as simply on a cell phone. So you can do it from your phone and you can really get involved in a lot of different ways. And we're going to kind of explore some of those in today's presentation. It's actually good timing for us to be talking about this because this month is Citizen Science Month. April is the month of citizen science. So with that, I'm going to pass it off to our guest speaker and our presenter today, Dr. Jeffrey Gerber. He is my research advisor, and I am excited to have him teach you about citizen science today. So I hand it off to you.
Here we go. All right. So welcome, everybody. Today, yes, I also, in addition to working with Dylan, I also work with Thomas and Brooklyn. They all work on research. We'll talk about the kind of research that my group does in a little bit. But first, I wanted to give a little background about myself and why I've come here to talk to you about astronomy and something that I'm actually really excited in, which is citizen science, especially, and getting amateurs to help with the scientific process. I think astronomy is especially something that interests a whole lot of people, whether or not you're in academia or just at home or just out at night looking up at the night sky. And that's how my first interest started in it. And so I think it's great that we have all these tools to let everybody who's interested in astronomy take part. So I started I first had my interest for astronomy like a lot of people. As a kid, I used to look up at the night sky. I lived in an area with pretty dark skies and we could see a lot of stars. And I used to wonder what the heck were those things made of? And so that's exactly what I went on to study. I went to school at a place called Appalachian State University, which is in the mountains of North Carolina. So this is an image of the university and you can kind of see it here. I'm not sure, you probably can't see my mouse, but I'm pointing in the building, sort of in the middle. You see there's this group of buildings with like these green roofs that are sort of lumps across. And right there, you'll see a telescope dome. And on campus at App State, there are actually telescopes that if you can see over the mountains and over the football stadium lights, you can get to observe with. And so I went to this school so I could study astronomy, so I could study the stars up in the mountains so we can observe. I spent a lot of my time then enjoying outdoor activities, going hiking and things like that. And eventually then I learned that, if I was an astronomer, I could not only enjoy the outdoors, I could go observe stars, but I could learn about the things that I was most interested in, which is stars, what they made of. So from there, I went to graduate school at Indiana University before going to the Max Planck Institute of Astronomy out in Germany, all studying stars and what they're made of. So a lot of the research I do involves using telescopes similar to these. So here's a picture of me with a couple of telescopes out at the observing site. So we normally keep these telescopes in places that we like to call high and dry. So the atmosphere, while it's great for allowing us to breathe, is not so good at looking through. So we tend to put telescopes up high on mountains so that way we can get as much atmosphere out of the way as we can. And these mountains tend to be dry places where it doesn't rain a lot, so there aren't a lot of clouds. So these mountains are up in the deserts of Arizona. That's where Indiana University, keeps its telescope right here that I've spent a lot of time on. This is the WIN 3.5 meter telescope. So you can see its mirror that it uses to collect light here is 3.5 meters across. And then similarly on that mountain is another kind of telescope I use. This one is about 4 meters across. And so I use telescopes about this size. We observe stars, we take their light, we split it up based on wavelength. through a method that some of you might have heard of before if you've, depending on how long you've been a part of Saturday morning astrophysics at Purdue. And we break that light up and look at stars spectra, and that helps tell us what those stars are made of. So similar to how a prism will create a rainbow, this telescope has some instruments on the back of it that do the same thing with that starlight. And based on what colors we see and what colors we don't see, we can figure out what stars are made of. And so that's a lot of what my research does. Specifically, the type of stars that I care about are stars that are the same sort of mass as our sun. So they have the same amount of stuff in them as our sun does, except they're a little bit older. And we go find these stars in these things in the galaxy called globular clusters. And so these are big clusters of stars. You can see an image of one there on the left. This is a globular cluster called M13. It's out in the halo of our galaxy, so in the outer regions of our galaxy, instead of the disk where the sun is. And so you'll see a lot of these stars there are red. And those red stars are similar to what's going to happen to our sun. So on the right is an example of that. Our sun is now one of those tiny yellow dots, and eventually will become this big red bubbling thing called a red giant star. And so to figure out what our sun is going to do eventually, we don't have time to wait around for it. Our sun is going to live for billions of years. So to figure out what it's going to do, we go and look at some stars that are like our sun, but a bit older. And that's what these stars are in this globular cluster. So it's an excellent place to go do research on stars, go observe older stars, and overall see how stars evolve over time and how they change what they're made of over time. So that's a lot of the research I'm interested in, is studying these red giant stars that you can see in this diagram. So stars that are low mass, like our sun, that start out as these yellow points and eventually become these red giants. So I study what sort of changes in that star as they go through that phase, as part of this whole diagram of different stars and how they change and evolve. And in the past, a lot of the research I did involved going out to the telescope and observing stars individually. But nowadays, with technology becoming what it is and being as advanced as it is, a lot of work that astronomers do no longer involves the old days of going out and pointing telescopes. And that's what's going to lead us into citizen science and where you can help out. And the other research I do involves now, instead of looking at these stars one at a time with a telescope, astronomers with automation and with computers now set up big surveys. And what these surveys do is we take a telescope and we just have it automatically look at as much of the night sky as it can on any given night until we can map out as much as we can of whatever we're trying to look at. And so the two surveys that I'm a part of, one of them is called Foremost. It's called Foremost because it uses a 4-meter telescope that looks something like this. So this telescope is about the same size as the one I showed before. You've kind of got a ladder there for scale. And it's going to set that up, and it's going to take spectra of millions to hundreds of millions of stars. So that way we can get as many stars as we can and look at all sorts of different types and see how they evolve. It's also going to tell us what kind of stars live in different places in our galaxy. In addition, I'm also part of a survey that looks for planets. So this is the Plato mission for planetary transits and oscillations of stars. And this one is going to figure out what stars are doing. It's going to look at the light of those stars and see how it changes with time and see if it can find, this is going to be a space-based telescope. We're going to launch it out into space, and we're going to try to see if we can find any exoplanets going around nearby stars. So again, this is something that's going to survey as many stars as it can. And so a lot of newer work in astronomy, especially in stellar research, involves these kind of surveys now. Instead of going out and looking at stars one at a time, we'll set up these kind of surveys that will go and take as much data as they can on any given night. So the problem with that is, as we'll talk about, these surveys create a lot of data. They create way more data than any one astronomer can look at by themselves. And that's where amateurs and citizen scientists can come in and step in. So looking at these surveys, what do these surveys look like? Well, while surveys have become more popular lately, they're nothing new. The idea to try to observe as many stars as we could to map out the Milky Way actually first was done in the 1750s by a sibling pair, Caroline and William Herschel. And they went out in the 1750s, and with their telescope, they mapped out all the stars they could see, with the assumption that the areas in the sky that they looked at where there were more stars were farther away. So they put the sun at the center and they just plotted out the kind of stars they could see and kind of just guessed that this was roughly a map of them. They noticed some areas where they could see a lot more stars than others. Those areas are these long fingers to the right. And you'll notice there's a sort of gap in between those two long fingers shooting to the right. That is actually what we now know is towards the center of the Milky Way, where there's a bunch of dust and gas that gets in the way and obscures a whole lot of stars that way. So that's why they didn't see any stars there. So while this was the first survey trying to map out all the stars, since then we've come a long way. And today, more recent surveys with space telescopes and larger telescopes, our map of the Milky Way now looks something like this. So this is our modern day map of the Milky Way. So this is a real image. This is a real image from a space telescope called the GAIA Space Telescope. And this shows our galaxy where we've got a bunch of stars. You can see all of the points in this image that are little dots. Those are all the stars in our disk. You can see a couple of nearby dwarf galaxies down there below the disk. To the right sort of corner, you've got the large and small Magellanic Clouds, or what we call these. We can't see them from the northern hemisphere up here. You have to go somewhere in the southern hemisphere on Earth to witness those. And then you've got all this dust in towards the center. And we know that our sun is sort of off to one side. So it's not in the center. It's actually off towards the left in the disk, in that sort of center part. So with survey telescopes, we've now been able to map our entire Milky Way and continue to study it. And the way we were able to do this, the way we were able to create this image, was with a telescope called GAIA, which is a space telescope that the European Space Agency launched, that the plan was to observe and get distances to and create a map of as many stars as it could. And so as of its latest data release just last year, so this is the GAIA data release 3, it has now observed one, and then you'll notice there's a whole bunch of numbers after that one. This is 1.8 billion stars. So it's observed over 1 billion stars in our galaxy. And you can start to see the problem that astronomers are having with this big survey. As far as professional astronomers are concerned, like myself, I want to study as many stars as I can, and there's no way I'm ever going to reach something like 1.8 billion stars. And this is where we need help from you and from anyone in the public who's interested in astronomy. You can put on your astronomer hat and go do some data analysis for us and tell us what you find in these kind of surveys. In 1.8 billion stars, there's a lot of weirdness. There's a lot of different kinds of stars. There's a lot of different kind of categories that we have to try to put stars into and figure out. There's in there, not only are there stars, notice there's over 1 million what we call extragalactic sources. These are points of light that come from somewhere outside of our galaxy. So those are things you're going to see when you're trying to observe stars. You're going to also see some things that are farther away. And so that's, again, an area where we need help classifying what are those sources that come from outside our galaxy. Are they galaxies? If they're galaxies, what kind of galaxies are they? And so this is just the most recent example, but this is a problem where we've got now these big data projects with more stars than we can handle on our own. Has been happening a lot, especially in the last couple of decades. So the GAIA is an example. This one was looking at stars to map the Milky Way. Another example that you might have heard of is something called the Kepler Space Telescope. So this one's made a lot of news lately, especially in the last 10 years, because its plan was to go out and look and find as many planets around other stars that it could find. And so you'll notice the numbers. It was out there for 10 years observing with 2 different missions, and it observed 530,000 stars. It's got over 600 gigabytes worth of data that it came back alone, was science data that had to be looked at, combed through. You had to look at all of these stars and all of these observations, which were observed for years at a time, to see if any sort of planets you could see going by those stars. And in that 2,000 plus planets were observed, a lot of those were helped. The way we identified those were through people, amateur astronomers looking through the data, given the data on their computer, trying to see if they saw any sort of planet go by. It's a lot easier to try to look at 500,000 stars instead of having 5 people try to look at 100,000 stars. You can get 100,000 people or more, each look at 5 stars and see if they see any exoplanets. So that's this idea that we're headed towards, that we want to get the public involved. We want to get as much data out there as we can. In addition to looking at stars and exoplanets, back before Kepler even, one of the first surveys out there was a survey called the Sloane Digital Sky Survey. And instead of mapping the galaxy, this survey's whole goal was to map our universe. Specifically, it wanted to map the galaxies that were out there outside of our own. So this was in the early 2000s. And what it created was this map on the left. And what you're looking at, every point in that map on the left is a galaxy. So all of those points are galaxies, and that is a distance map. So that is a 3D representation. Basically, we put the Milky Way at the center there. And as you go up in that fan, you are going farther away from the Milky Way. So you're going farther out in space. And so we wanted to map where galaxies were. You can see where galaxies aren't, to give us some idea of where galaxies form in the universe, how they clump up, what they look like. And so what it did is it took a bunch of these 2D images of the sky that you can see sort of inset there. And every point in that image is a different galaxy. And so it wanted to basically look at as many galaxies as it can, look everywhere in the night sky, and try to create this map of where galaxies are. So they did this. They went and looked at a bunch. This was the Sloane Digital Sky Survey. They looked at a bunch, and they quickly found out in the early 2000s that they had more galaxies than they could handle. So looking at what this telescope looked like, and I wanted to show it because I think this is a cool telescope. The Sloane Digital Sky Survey, here's the telescope here, and you'll notice compared to those other telescopes I was in where there was a dome around them that sort of shields the telescope, this telescope looks like it's out in the open air. And that's because, one, it was designed to look at as much of the night sky as it could. So they didn't want to have something like a dome in the way as this telescope slewed around and tried to observe any different location that it was looking at as it automatically went from night to night. And so the way they did that is instead of the building having an opening in it, the building itself slides off of the telescope. And so I actually wanted to show this real quick. They have a video of it, and I think it's really cool as they're getting set up for the night. So what they're doing is they're placing in their sheets for the night that's going to tell the telescope where to look at and help collect those observations. The scientist parks that information so they can collect it later, and then they slide the whole building off the top of the telescope there. So it's really quick, but the building starts on top, and they slide the whole building off. I'll show it again. And then the telescope is ready to observe at night, and it doesn't have to have that building in the way. So then throughout the night, SDSS, you can kind of see this video shows it pointing at different locations as it goes around and looks whichever place it wants to look. And it observes as much of the night sky as it can. And in doing this, they did an excellent job collecting a whole bunch of galaxies, but the scientists wanted to categorize those galaxies. And so they ended up with 1 million different galaxies, and they had to categorize them all. And one scientist, after going through 50,000, had talked about how numb he had gotten to the whole process and how it was clear that this was going to be something that was going to take them decades if they tried to do it alone. So they realized that what they could do is instead reach out to the public. And this is one of the first citizen science projects in astronomy, or definitely one of the ones that made it so popular to do. Because what they found out is by asking the public to help, they were able to classify over, I think they got something like 50,000 categories in the first hour, as opposed to something that had taken an astronomer years to do. The public really liked it. And what they did is they just presented images just like these that you're seeing to the right that came from Sloane of different galaxies. And then they asked the public to sort those galaxies based on what type they were. Were they an elliptical shape, like these in the top row? Did they have spiral arms, like these in the next couple of rows? Did they have a bar going through the center, like these in the last row that you can see? And it turns out, while it was difficult to try to do those by themselves, and this is something that you actually still can't train a computer to do. Computers are really bad at doing stuff like this, at putting things into categories, especially at figuring out where weird things go. But we need to categorize these galaxies so we can learn about the types of galaxy formation that's out there, what these galaxies went through in the past. And it's much easier to just have amateur astronomers come in and do this. It's easier to set them up with a tutorial, show them a bunch of pictures of galaxies, and have you categorize them and be the astronomer for the day. And in being an astronomer for the day, you can classify something like 20 and do something to add to the scientific process. The Sloane Digital Sky Survey was able to classify all of their millions of stars in a year, something that would have taken them by themselves, multiple years to do. They were also able to then continue this work. And so Galaxy Zoo, as this project was then called, has been going on since 2007 now. As more and more telescopes observe more galaxies, we have the public, amateur astronomers, come in and classify those galaxies. So that way we can learn about what galaxy, where they go to, how many of a certain type of classification there are, things like that. So that's what we're going to start with today. We're going to actually look at Galaxy Zoo that's still up, and we're going to classify some galaxies, and we're going to contribute to the scientific process, like I said. So this work doesn't just get shelved. These Galaxy Zoo work has over 450 publications. So tons of publications that all make use of this catalog, this database that they've built. So that's this Galaxy Zoo work that I was mentioning. Here's their whole logo. We're going to send you to the site that they launched with the hope that they could classify all of their galaxies that's still up and running. Like I said, more than 50,000 classifications in the first hour and more than 50 million classifications during the first year by 150,000 people. So citizens are out there contributing to the scientific process all the time with all of these projects. Since Galaxy Zoo, other projects have done the same thing. I talked about Kepler sent its data out so that way people could find exoplanets. Other data is out there looking at planets. We'll talk about some other data looking at the sun today. So we'll look at a couple different projects. We'll show you where you can find these projects. So you can go on, you can put on your scientist hat, your astronomer hat, and go help contribute to science and help us out with all of this data, right? So that's our first little session here. We're going to step out into some breakout rooms and have you go and classify galaxies. And so there's two different Galaxy Zoo projects that are up right now. We'll show you where those are. There's one classifying the galaxies you'll see, and there's another that they've actually launched even for phones now, Galaxy Zoo Mobile, where you can look at different galaxy features that you see. And so you'll get a chance to do one or the other or both in your breakout room and just have some fun with the data out there.
Yes. So before we jump into that, who has a question about anything that we just went over?
Yeah.
Either myself or Dr. Gerber. Does anybody have anything that they want to ask us before we jump into the breakout rooms?
Sorry, yeah, ask those questions before we head out.
All right, and then you may have noticed that Thomas put a link in the chat to a website called Zooniverse, and that is where we're going to be going. And then the TAs will also be able to give that to you in the breakout rooms as well. But we'll go ahead and get those started and start classifying some galaxies.
Cool, awesome. So we'll just click smooth and then next. And so then we'll see how round is it? Completely in between, or is it more cigar shaped? What do you guys think? In between? That sounds about good to me, I think. Yeah, cool. So we'll just click that, next. So is this galaxy merging or being disturbed? So you can see merging, major or minor disturbance, or nothing's occurring to it. So what do you think is happening to this galaxy? Daniel says merging. Val, Jessica, do you guys have an opinion? Merging? Cool. I agree. Okay, so for this image, do you guys see like a sort of lensing effect with the kind of like what that image is, if you can see it, kind of like a sort of lens around it? Is there a ring? Does it look somewhat irregular? Does there look to be dust covering some of the galaxy? Overlapping. Oh, is there something like in front of the camera that looks to be not part of what we're looking at, but it's covering up some of it, or something else going on? Do you guys see any of these features?
This one's a little tougher than the other ones we did.
Mm-hmm.
I mean, it looks like it could be a dust lane, but not entirely sure.
It could, yeah. Daniel says he doesn't see anything. Maybe irregular or dust. Mhm.
Okay.
So what should we put then? Can we do multiple? Oh, we
Oh, we
can.
can.
Oh, nice.
So I'll just put 3.
Right.
Okay, so then we've picked everything we want. If we want to go back and double check things, we can. And then we click done, and then we're given a new picture. So you guys can go ahead and do this on your own as well. Do you guys want me to keep going or let you guys go on your own?
We could maybe keep sharing the screen and then have everybody do some on their own too. If
Cool.
anyone has
Yeah.
any questions, we could always get to that point.
Sounds good. Do you guys see any cool ones? Daniel or Val or Jessica?
Mariana, I think you have something really cool up right now. It seems really
Mm-hmm.
bright compared to the other stuff we've done so
Yeah, it
far.
does. Daniel,
Ooh,
are you able
interesting.
to share your screen?
Let's see if I can.
Cool. Thank you.
That's most likely just going to be a bad image.
Yeah, probably.
But, classifying these bad images are still good because it gets crummy data out of the stream.
Yeah.
This one looks interesting.
What do you think this one is?
The features disk.
Features? Mm-hmm.
Yeah, I'd agree with that.
Yeah.
You guys know what edge on means?
No.
Yeah. So edge on means when we're looking at a galaxy, it's going to look different depending on which way it's oriented. So galaxies are flat a lot of the times, but if it's edge on, we're going to be looking directly at this plane. If it's face on, we're going to be looking at this. We'll be able to see a lot of stuff from the way it's oriented. So essentially, does it look flatter or does it look more like we can see a lot of stuff in it?
It's kind of a bit of both.
Yeah. Yeah, so
I guess
I agree.
it kind of looks like it has a strong bar across the middle. Or a bit of a bar.
Mm-hmm. Yeah, I think so
Yeah.
too.
I agree.
You guys are good at this.
Yeah.
Catching on really quick.
These are medium or loose. Doesn't look pretty tight.
Yeah, I'd agree. So this is a little difficult to tell because the main arm that we can see is kind of coming from the back. Yeah, you have your cursor on it there.
Yeah, it looks.
So yeah, I don't know. I mean,
I mean,
I
but
think
it's
it could
not
be.
super wide. So
I'll
That's
just go
true.
with medium.
yeah.
Yeah, that sounds good.
Yeah.
It doesn't look like there's one in front of it. It only looks like one.
Mhm.
Yeah, I can only see
Yeah, I
one
think so
really.
too. Well, you just classified your first
Yeah.
real astrophysical data. How does that feel?
Pretty good. It's kind of cool.
Yeah,
Yeah.
yeah, it's a good feeling.
I think you're a galaxy hunter in the workings.
Oh
So
yeah.
yes.
Yeah, you guys all did really well.
Mm-hmm. Yep. Cool. So we can go ahead and go back to the main room and we can learn about another one. Thanks, guys.
Yeah.
Okay, yeah, I see thumbs up. So I'm going to pass it back off to Dr. Gerber, and he's going to introduce the second project that we're going to go through. And yeah.
Okay. So we looked at classifying galaxies and galaxies features. As you saw on Zooniverse, there are a whole lot of projects out there, and it's not just limited to astronomy. Citizen science has been going on for a long time. Astronomers just realized that they could take advantage of it with all the data coming in from these new survey telescopes that they were getting, that they definitely needed the public's help. And astronomy is such a science that, the public appreciates, that we all sort of enjoy, that we like. And so it's something that it's great to have the public as involved with as possible. But you can see there's all sorts of not even astronomy projects. So maybe classifying galaxies isn't, something you're interested in. There's a bunch of different, looking at disks around stars, looking at asteroids, looking at sunspots, looking at these things called kilonova explosions. There's also a bunch of different projects then if you're interested in a different type of topic. There's physics projects, biology projects, especially there's a squirrel mapper, which is literally they're trying to classify all the squirrels out there. They know people tend to see squirrels in their yard, and so that sort of project is having people basically observe all of the squirrels that are out there in the US at the same time so they can figure out where squirrels are going, where they might be migrating, things like that. Bird migration and bird watchers have been big citizen scientists for a while. So there's all sorts of things in ways that you can help and be part of the scientific process. There's types that we're going to talk about. We talked about galaxies as one. We're going to focus on one more here, and that is the Solar Jet Hunter project. So there are basically two types of projects that have more data than professional scientists can handle. One type is like what we talked about, where we're trying to observe millions to billions of objects and classify them and find anything weird in there, and things like that. And so that's obviously too much data for one sort of scientist to handle. The other type of large data set is, instead of looking at a lot of things, there's data sets out there that look at one thing, but look at it for a very long period of time. And so they end up with a lot of data that way. And one of those projects is this Solar Jet Hunter project, where we've taken images from the sun, where this project has been observing data from the sun for the last decade. So you can see some of these images are coming from 2012. So the last decade or longer. And the idea is trying to study the sun's activity. So we know the sun is active. We know that every now and then it shoots out these jets of material that you're seeing all sorts of images of here. And those jets of material affect the solar wind. They shoot high energy particles that head towards Earth, and that overall affect the sun and how it changes and how it evolves. And so we want to study and better understand that. We want to understand that for all stars. And the best way to do that is to look at the star that's closest to us, that we have the most data on, where we can actually see these jets. And so to understand the physics better, we want to classify all the different types of jets that the sun has had. How active has it been? When has it had more jets than others? When did the jets occur? But over 10 years of time looking at the surface, that's way more than one person to look at. So this project is again asking for help, asking you to try to look at the sun and find jets on it. So we thought this was especially relevant. We just saw the eclipse. So we just had a chance to look at the sun and see its exterior, the corona. As you were looking at the eclipse, those of you that said you saw it, you might have seen some really bright pink spots out there on the edge. Those were these things called prominences, which aren't these jets that are shooting out, but are instead these loops that you can see in the top left image. Just below the jet, you see that sort of loop of material. That's what we were seeing during the eclipse as well. So that was a chance. We've already studied, or you've probably seen some of these, and now is a chance to go and find more. Find the sun, these chances, where the sun has ejected a bunch of material, so that way you can help scientists classify it. They can see how long these jets last and use it to constrain their ideas and theories about the solar science. So we're going to head out to breakout rooms again and look at this other project.
Go right here down to this page, and then this has a little bit of a different format than the last one we looked at. It has everything still there. It has the information, it has the statistics still, but to actually get into this one, you're gonna have to click on box the jets, which it has 55% complete here. And like Dr. Gerber was showing, this one is just a video. So you have these videos that you'll be able to go through and look for things like that, where it has something shooting out of the sun. Now, this one's got a lot going on, and I need to move my little zoom bar out of the way. We'll focus on the second one for this. So yes, there's a solar jet in this video, and then it's going to bring you to a place where you have to mark it. So you have to kind of scroll through the video and find it, and we'll just focus on this second one here. Right at the point right before where it starts. And on the right side here, you'll see that this green kind of crosshair is selected. So as I scroll through it and we see that jet start to form, you can drop the crosshair just in the moment before it starts. And then as it goes away, in this case, it's the end of the video, so we don't get to see it disappear. You'll drop this blue crosshair where the jet dies or disappears, where it ends at the very bottom. And then what they want you to do with this jet is back up and find the time where it's most prominent. And I would say that's kind of right before the end here, and actually put a box around it. So kind of highlight it And all you do is you just click and hold to drag this box around. Then you can change the size and shape, the rotation of it and the position, all those things where you can highlight it. So by the end here, I have this image where I have my starting point, my end point, and I have it boxed in. And when the researchers go back through and look at this video, they can find it. And is there another jet? Yeah, there's the one that it starts with, but for the sake of it, I'll just pass that on here. Does anybody or who has a question about that kind of process? Does that all make sense, or is everyone able to go through that and understand what we're going through here? This one's a short one, so you get that big thing, and then again too, if you're confused at all, the field guide is in a different spot, so it's not off on the side tab. So you can go through and you can pull up different examples that they have of the various things that they're looking for, whether it's, whether it's a flare, whether it's a jet. In this particular case, they're looking for jets. So if you see something like a prominence, like Dr. Gerber talked about, or that you might have seen on close-up images of the eclipse, this one in particular is just looking for those jets. So are there any questions? Who has a question about anything that I've just went through there? I will also make a note before we get too far into it. For this project in particular, it will only let you categorize a handful before it stops you, and then it'll ask you to make an account. This is the only project that we've seen that on. So if that happens to you, let us know, and then we as the TAs will share our screens and we can go through some together. So does that make sense to everyone? Is everybody good? Any questions, Anish or Mari? Yep, I see thumbs up. Good. Akshat, do you want to share your screen and we can go through some that pop up on yours here while we're
Yeah, I was gonna say I found something interesting, so
awesome.
I want to know your opinions on it. So the different kinds, like Dylan showed, there's different kinds of jets here. Does anyone have guesses as to what this might be? What are we looking at?
I know first getting into it, it might be like, well, it's a short
Yeah.
clip, so you only get a little look at it. And you might be
Very,
and like Akshay showed, this is where that field guide comes in a huge hand. So who has a guess for what that might be? Is that something you think we should highlight for this project, or do you think it's just a weird thing that happens where it just gets brighter for a second? Yeah, and Anish, any thoughts on this? Okay.
I think it might be maybe like a solar flare.
That's a guess. Yeah, I think I would personally myself, I would have to go through the field guide a little bit because it looks like a couple
Yeah.
of me. So that's a good guess.
yeah.
Mari, you agree? Any other thought on that? Kind of feeling the
No.
same way about it.
Yeah, I agree.
You agree? All right. Rowan, same thing. Yeah, nodding head. So, Akshat, is there a solar jet? What are we gonna say?
No.
Yeah, I'd say that's a flare. So, ooh, this one looks fun.
Yeah. 5 seconds. All right, this is a much longer one. Okay,
Interesting.
bit of a longer clip. You see something there.
So yeah, just a quick comment on what we're kind of looking at. It's weird how it's all kind of like swirly and twisted, isn't it? You guys
Yeah.
notice that how it in that weird area? Does anybody have any idea why it might be like that? Why the sun might appear like that when we look at it really closely like this? What's causing that kind of swirl that you can see there? So a lot of that, and a lot of things with the sun boils down to magnetic field. So the sun has this really complicated and strong magnetic field, where a lot of cases these fields run along in lines, and in a lot of cases those lines get twisted and tangles. It's what causes those prominence. It causes flares and things like that. And what you can actually see how that affects the surface of the sun, and you can actually visibly observe it. So In a lot of cases, you'll see a lot of this twisting, and that's what causes a lot of this jet behavior and a lot of these flares and things like that. So yeah, this is a really interesting one. But back to jets, who thinks we see some jets here? Anyone? Do you think there's one or more jets in this? Dr. Gerber, you just came in. What do you see?
I think there's a jet right there in the center.
I think so too. There's one right here.
Yeah. We can see the
One on
little
the left.
material kind of, and the key is not only is it brighter there, but as that video played, you saw a little bit of material kind of eject out right there.
Rowan, you were saying something. What were you?
It looks like there's one on the left as well.
On the
Do we find
left.
another two?
Kind of over there. It comes in towards the end.
Yeah.
Oh,
Yeah,
you're seeing this right here?
Yeah.
Okay. Yeah.
So this one,
This
and
is an
then
interesting one.
yeah,
So
just
I'd never seen 2 in 1 video yet, or I hadn't yet. And the last group just found one, and we've got another one
You
here.
think this
because
could be
I popped
one?
into this other group.
that one's tricky.
Yeah.
That kind of bright.
You can talk, yeah, and the field guide there will tell you the difference between different types of activity we see on the sun, whether it's a jet or a jet on the disk. The widening, the reoccurring, it's got all these different types of jets that you'll see. I think if you scroll down further, it might have these prominence.
Okay, welcome back, everyone. So, what did we think about solar jet hunting? Did we find anything interesting, anything cool? Who saw something really, really weird? Or who found multiple jets? Anybody find multiple jets in any of theirs? Yes, yes, no.
Daniel, I know you did. You found
Daniel,
a
yeah.
good one.
Yeah, Daniel, 2 jets. Rowan, we had one that we pulled up on in our room that had 2 jets. So good. So yeah,
Someone
there's
found one with 3. That's impressive.
yeah.
Cool.
So yeah, this is one that you can go through. This one's a little bit more interactive. I like it a little bit more than Galaxy Zoo personally. But as we kind of showed, and I believe the TAs probably went through it too, there are dozens of projects that you can look at and go. One thing I didn't mention, and Dr. Gerber hadn't yet, is that because there's only so much data to go through, and conversely, there's a lot of data coming in. These things turn over a lot. So when we were planning this out, we had to kind of pick things that were going to be available to us to look, because you run out of data, people classify everything. Galaxy Zoo gets updated a lot, but and there's tons of solar data too. So these two will probably stick around for a long time, but a lot of them sometimes are paused or retired until new data can come in. So it's great that we have this huge influx of data, but just keep that in mind that you may go in a week and there will be completely new projects that they've never done before and we'll be able to look at.
The black hole hunter, yeah, that one has looked interesting to me. I've tried to look at that one. There's another one I'm going to look at, which is talking about Gaia variable stars. So that's in that Gaia big survey. Basically stars that they saw out there that were doing weird things, and asking you to help them classify and figure out what those weird things are. So a lot of different projects.
With that, thank you all for coming to Saturday Morning Astrophysics at Purdue, and we are going to sign off, and I believe we're going to do a May session as well, aren't we, Dave?
I think we have one planned. We're going to go all the way through the summer.
All the way through the summer. We've never done that before. So, yeah, thank you for joining us, and we hope to see you at the next ones. Bye, everyone.